Okay, now I think now it's time. So let's start today's seminar. We are very happy to have Ennio Slavioni from Padua, University of Padua, here to talk about bouncing dark matter. Please start when you're ready.
Okay, thank you very much for inviting me. It's really a pleasure to give this talk. And I want to say two things. First, if the audio isn't so good, please stop me. And the second is feel free to interrupt with any questions at any point, because this would be ideal for me. So this talk is indeed about a recent paper that we finished with Josh Ruderman, who's at NYU, Bibhushan Shakya, who is at Daisy, and Lucas Puetter, who is in fact a student of Bibhushan in Hamburg, or used to be at least. Now we moved, but. And the second reference here in parentheses is just a previous paper that was a bit of an inspiration for this work. Okay, so I'll come back to it, but mostly it's based on this recent paper. Okay, so okay, now you can see the change. So the introduction will be very short in the sense that this talk is about thermal freeze-out of dark matter, which is a picture that we know very well, and it's still a very well motivated possibility for explaining the origin of particle dark matter. So this is just a sketch of dark matter on the left, which I will call chi in this talk. This will be actually constant, so chi is the name I'll give to dark matter. And this is a process of annihilation to the standard model with a coupling lambda here, and we know that essentially the observed Rayleigh density of thermal dark matter is obtained in this scenario for weak couplings and weak scale masses, very roughly speaking. That's a ballpark where we get, which goes under the name of the WIMP miracle also. And of course, this is a very intriguing observation. It has been studied in a huge variety of contexts, and this is just showing the standard picture. So as we increase the cross-section, the thermally average cross-section for annihilation to the standard model, we follow the equilibrium distribution for longer, and so the final density, the one we observe today, is smaller. Okay, this will be important for this talk. And so, as I was saying, this is a framework that is very well studied. Okay, there are many interesting variations, and I didn't even try to reference them because, of course, it's impossible. But one thing that is true in general is that the typical picture is that the dark matter follows an abundance distribution up to a point, okay, which is an exponentially decreasing curve. And then when the interaction rate goes below the Hubble rate, it just becomes constant. Okay, that's the freeze-out mechanism. Okay. And instead, here, what I will discuss is slightly different. Okay, so what I will discuss is something that looks like this as a sketch. So this is the Y is the comoving number density, so the number density of dark matter divided by the entropy, which factors out the expansion of the universe. And you see, we do follow some equilibrium distribution, then we depart from it. Okay, but then the dark matter abundance grows. Okay, it goes up exponentially, in fact, in time until it really freezes out finally. Okay, so the freeze out is here, and this type of mechanism, we called it a bounce. Okay, for clear reasons. Okay, and so it's really the transition from an exponentially decreasing equilibrium curve, which is here, to an exponentially increasing equilibrium curve. And here it's important that we are indeed remaining within equilibrium, as we will see. Okay, so this is the idea. So this is what I will talk about here. And concretely, what I want to say is a few things about the mechanism. Let me first say that we took inspiration for this. We observed this kind of effect in this paper here. Can you see the cursor? Yes, you can.
Yeah,
good.
We can. Yeah.
So this paper was for us the origin. Okay, we observed this mechanism, although it wasn't really for dark matter. It was for another dark state, but the physics was somewhat similar. But also, of course, this has been studied by in fact your group in other papers, in particular these two references, which I put here. And so it's particularly interesting for me to speak here, and please feel free to interrupt at any point. So this is the sketch, and so what I want to say in this talk is a few things. So I will start with the conditions for the bounce to happen. So under what conditions can we observe something like this? Okay, and then I will show some explicit realizations, okay, in sort of toy models. These are really not UV complete models, but just simple setups that allow to see the physics. And I will outline some implications for observations, so for phenomenology of dark matter. Okay, so this is the plan for the rest of the talk. Okay, so what about the conditions from the bounce? Okay, so the general statement is that the bounce can happen in scenarios where there are other states together with dark matter. Okay, so in a sector, dark sector, there is no minimal, as is often studied. There are other states, and these can participate in the bounce. And for tracking the evolution of the densities in the dark sectors, here it will be useful to use chemical potentials. Okay, so in the non-relativistic regime, for temperatures below them, the masses of the particles, let me essentially define the chemical potential in this way. So the number density will be e to the mu over t times the equilibrium number density, and the equilibrium number density has just the standard form in the non-relativistic limit here. And what is true in general is that if a certain reaction, let's say a state A and B going into C and D, is rapid compared to the Hubble rate, then we have this relation. So the sum of the chemical potentials on the two sides is equal, until, of course, this relation goes sub-Hubble, and then this will not be true anymore in general. Okay, and so one first observation is that if dark matter has the same chemical potential of another species, which is lighter, so let me call this A. Okay, this is another dark sector particle that is round. If the dark matter has the same chemical potential, then we're not going to get a bounce, because the dark matter abundance will keep falling exponentially. And this you see by saying that if mu chi, so mu of dark matter, is equal to mu of this other state A, then the number density of chi is written in this form. This just follows from this equation. And so there is this factor here, which is an exponentially falling distribution. M chi is larger than MA by assumption. This is a lighter species. And so this keeps dropping essentially. And so we're not going to get that. So as we will see explicitly in all the cases I will present, the chemical potential of dark matter needs to be different from the one of other species. That's the first requirement that we are going to see at play. Then there is a second condition, of course, which is it's not enough that mu chi becomes different from say mu A, but also that the chemical potential of dark matter itself rises sufficiently fast. Okay, and intuitively this is just because here in this Ni equilibrium there is an exponential suppression, and so this mu here has to grow fast enough to compensate for that. And if you take a derivative of the yield, okay, of y n chi over entropy density, you get this condition. So the chemical potential of dark matter has to satisfy this equation, and in particular the key factor here is this one. So the derivative of the chemical potential with respect to temperature has to grow quickly enough to allow for this inequality to be satisfied. This factor here you can essentially neglect in first approximation. So this is really asking that this sum is larger than the mass of the particle. That's what this is. Okay, and so let me a bit summarize these two conditions, which we'll see later in the talk. So really the two things that we need are a chemical potential that is different from other species, other lighter species, and a chemical potential that rises sufficiently quickly with time. Okay, so now this is a little bit abstract, so I think it becomes easier and much more intuitive if we just put it into some simplified model. So I'll do that, which is also what we do in the paper. We mostly focus on this model that I'll describe. But let me first stop and see if there are any questions on the general approach or other comments.
Maybe I missed. What was the X?
Yes. Thank you. So X is defined as the ratio of the dark matter mass. Let me go here. The ratio of dark matter mass to temperature. And in fact, that's good that you asked, because this will be the same throughout the talk. So of course, in these dark sectors, I have several masses, and I will always define X as m dark matter over T. Okay, it's just tracking time, inverse time, in a sense. Okay. Inverse temperature. Apologies. Yeah. Thank you for. Yeah, this is good. This is good. Please. Let's keep this informal. Okay. So. The simplified model that I'll discuss is a model that has 3 states. Okay, there will be dark matter and there will be 2 other particles, and it looks like this. Okay, so let me just take 3 scalars. Okay, and chi is again our dark matter candidate, and then there will be 2 more, which are phi2 and phi1. Okay, and I just basically decide that this is the mass ordering. So the dark matter is the heaviest. Then we have phi2 and phi1 ordered in this way. Okay. What I will assume, which is specific and important, is a certain type of interactions. So let me go through this Lagrangian. This is really all the Lagrangian that we need, but it's important. So here we have 3 terms, 1, 2, and 3, which are just quartic couplings that couple 2, say, chi's and 2 phi1s, or 2 chi's and 2 phi2s, and so on. This is just a 2-to-2 interaction between the different species. But then we have this one, this last term, that is important. This, you see, is a coupling of 2 phi2s, 1 chi, and 1 phi1. Okay. And this one in particular mediates interactions like indeed chi phi1 to phi2 phi2. Okay, by definition. And this is the specific one that will drive the bounds. And the assumption that I will make about the masses is also this one. Okay, so that 2 m phi2, so the right side of this equation here, phi2 phi2, is heavier than m chi plus m phi1. Okay, this will be important. And now one thing that of course is reasonable, you may look at this and think this is very ad hoc, and this is why it's good to recall where this comes from. So we really observed this in a previous paper in a SIMP model, where these states were dark pions, essentially. And these conditions are really realized by symmetry there. So I'll come back to this. You can get this in a scalar theory from symmetry principles. So for now, let's believe this in a sense. Let's take this theory and see the consequences, and then I'll come back to several aspects of it, which are important, but not for the mechanism. So for the mechanism, this is all we need to be present. So this is the content. And so the dynamics looks at this. First, let me flash how the behavior looks like. So this is Y, the co-moving number density, versus X, which is this mass of dark matter over temperature. And so you see these are the 3 states, phi1, phi2, and chi. Chi is in blue. And you see this bouncing behavior that I was already advertising before. Okay, so you see this rise here. And in particular, you start seeing several phases of the evolution, which I will discuss. So here, this is the key moment. This is what we call the bounce, XB. And this is where there is a departure from this equilibrium curve, and then the dark matter eventually starts rising. And then this is the freeze-out, actual final freeze-out, if you wish, in this setup. What I just want to observe here is that we can look at this plot and already see that the enhancement that the bounce brings, okay, which is going from basically here to up here, is really large. Okay, so it's several orders of magnitude that one can get, which of course is interesting because you can already imagine it will change the predictions for dark matter signals, because we do have an annihilation cross section that is very different from the thermal one in principle. By thermal one, I mean the standard value, which would be about 10 to the minus 26 centimeters cube per second in the WIMP scenario. But we'll come back to that. This is just to flash the picture. And so let me now discuss a little bit this dynamic. So how things go with time. So this is the same plot, okay, just shifted. So let's start from the left. So at very early times, what we assume is that the situation is relatively simple, that the dark sector and the standard model are in equilibrium. They are both in chemical and in kinetic equilibrium. There are just processes like this one. I just drew phi1 to standard model. Okay, you can choose many options, but this is one of them. And so this is really the standard equilibrium distribution with zero chemical potential. Okay, so in this phase, there is no chemical potential for any species, and they just follow the equilibrium distribution at early times. At here, which we call XC for chemical, what happens is that the dark sector and the standard model have a chemical decoupling. Okay, so this portal interaction, which you can think of, for example, of a Higgs portal, but there are other possibilities here. It's not really very relevant. You enter what we call the chemical phase. Okay, in this region here, there is no chemical equilibrium anymore between the dark sectors. And so within the dark sector itself, the total number density is conserved now. There are no number changing interactions anymore if you look at the total number of dark states. And so we have this chemical phase where interactions of this type, so AA to BB, so for example, two dark matter particles coming in and two phi ones going out, these keep all the chemical potentials equal, but now they are different from zero. Okay, and you see this right away because you see that this is not the same equilibrium curve as before. The difference in slope is really the chemical potential, the common chemical potential of the states. So in this case, there is sort of a shifted equilibrium curve, as is written here. It's just shifted by the chemical potential, and this goes on for a while up to this point here. Okay, so this is now the next phase, which is the bounce. So what happens here is the following. So once we get to XB.
Sorry,
Yes.
very naive question. If you say the number density in the dark sector is conserved, why do the curves drop so drastically then? I mean, this is not not just expansion.
Right. So let me just go back to I think the best is just to look at sorry, I have to go back here, but so this is what we are seeing here in that phase, in that region, is really just this one. So there is an exponential that is falling from the standard Maxwell-Boltzmann distribution, but then you get also this common factor here. Okay, so that you don't change the total number. Okay, that's just diluted essentially by a factor that is now modified by mu. Does the answer?
No, sorry, if you don't change the total number, where does the yeah, I just don't see that in the plot, that you don't change the total number. The number of phi 1 is completely constant, and the others drop drastically.
Well, no. So if you, yeah, okay, this is, I think, an effect of the plot. You see, this is constant simply because it's so much larger than, it's not really constant. Okay, it's also falling
I see.
itself. Yeah. So if you, I understand the question now. Yeah, if you look at the total number, which I don't have a plot for, but that's fair, you would see the total number is conserved. Yeah. Okay. So that's the statement.
Okay. So and here in the plot, you have you factored out the expansion of the universe somehow, or is that really?
Yeah. So this Y is defined as the number density divided by S, where S is the total entropy density. So that would be some constant factor times T cube.
Ah, right. So essentially, for a particle that is totally frozen out, you would really have exactly a horizontal line, right?
Yes. Correct.
Okay. No, but then, sorry. Then this phi 1 curve actually has to increase if the total number density is supposed to be constant, right? You can't have 3 curves falling and the sum of the curves being constant.
Yeah. Okay. I understand what you say. Yeah, morally speaking, yeah. So morally speaking, this is a constant to some extent, but yeah, I see. You say there is a very tiny effect that compensates for these two here in this plot.
Okay, so essentially the red curve goes a little bit up.
It in fact does. I mean, I agree with what you say, but also I'm trying to remember from looking at the plots. Yes, I think it does slightly go up. Yes.
Okay, very good. Then
no, thank you. Yes, this is important. Yeah. So yeah, in a sense, I should have a plot that zooms in and shows that it's actually true. I don't have it, but morally, that's true. Thank you. Yeah, very good. So please do stop me. That's very good. And Okay, so here is where we got. So we discussed this intermediate phase that was just asked about. And now let me move to what happens next, which is really the key point here. So once we get here to XP, then most processes decouple, okay, in the sense that interactions of the type A to B go out of equilibrium, and also the interaction that is coming from our extra vertex, which is, for example, chi phi 2 going into phi 1 phi 2. Okay, this one also decouples, and this is when the bounce happens. Okay, this is the time that we define as a bounce, because what happens after in this region is the following. What happens is simple. In fact, is quite intuitive. It is that the only interaction that remains active in this region is this one here. So phi 2, the two of them meet and scatter to produce a dark matter and a phi 1 particle. Okay. And this is what is important here is that this relation that I wrote here is kinematically open. So we have assumed that twice the mass of phi 2 is larger than the mass of chi plus the mass of phi 1. Okay. So this is a process that is in fact does not have any thermal suppression. It just can happen even at =0. And so in this phase, what happens is that there are many more phi 2s around than chi's. As you see here, there's a difference of perhaps 5 or 6 orders of magnitude at this point. And so it is very favorable for two phi 2s to simply produce dark matter. Okay. The inverse process instead, chi phi 1 going backwards, is suppressed by the mass splitting. And so once we go to low enough temperature, this is really producing a net amount of chi's. So we do get chi's, phi 2s, if you wish, converted into chi's. So this is the bouncing phase. This is the diagram driving this. And this is what I said in a more precise way. So the bouncing phase is really controlled by this process, which in the forward direction is kinematically allowed, but is not backwards. And so once the temperature is sufficiently low, we do get that chi phi 1 is the preferential choice in this reaction. Okay, and so this is effectively a transition to an exponentially rising curve. That's the bottom line. Sorry. And this is the top plot is the same that I showed. So again, yield versus x. But now we also show the chemical potentials of the species. Okay, so this is mu normalized by the dark matter mass. Okay, this is just a normalization to make it dimensionless versus x. And so what you see here is really a transition from one equilibrium curve, which would be all chemical potentials are equal. This is this region here. Okay, to a second, and you see here. Okay, same. And then at some point at the bounce, what happens, if you could phrase it this way, what happens at the bounce is that the chemical potentials become different for the species. And the new condition they satisfy is this one, which is dictated by this relation for chi phi 1 going to phi 2s. And so you see here now chi has a chemical potential that is way bigger than phi 2 and phi 1, which was something that we mentioned before. They have to be different. And also you see that it rises sufficiently fast to really enable this effect. In fact, it's good actually to look at it a bit more in detail. So the dashed black line here, the dashed black curve, this one, which I hope you can see, this would correspond to a constant y chi after the bounce. Okay, and instead, in fact, what happens is that initially the chemical potential is a bit below it, then there is really a phase where it's above, and so it does grow, and eventually asymptotically flattens out again and freezes out. Okay, so this is really reflected in this plot here. Okay, let me stop again. Any more questions, comments?
Hello?
Yes?
I'm Louis. Let's present my paper. And so how do you guarantee the chemical equilibrium during the bouncing phase? I mean, because at low temperature, the background process is Boltzmann suppressed, right?
Yes.
So, I mean, so how do you guarantee the chemical equilibrium during the bouncing phase? It is because the mass difference between the initial state and the final state are small?
Yeah, of course, yeah, you do have a finite range of masses where this can work indeed, because you need these two conditions that I was showing before. But let me understand the question. So you're asking, because in this case, let me go back. Sorry. So this is the process we're looking at. Okay.
Yeah.
So the statement. Yeah, please.
Yeah. I mean, because at the low temperature, right, the backward process get Boltzmann's press, right? Because if you want to make a chemical equilibrium, then both the forward process and the backward process should be, I mean, both active, right?
Yeah. So I understand. Okay. I understand. So, in some sense, I think what happens, the answer to your question is that this relation that I write here, so the fact that this is in full chemical equilibrium, and so we get really this relation of this. Sorry, here, it's here. This relation here, it is true. It is true up to a point, yes. So of course, it's true that eventually, when this one is completely, the backwards is completely shut off. Okay, you don't really have chemical equilibrium anymore. Of course, what we do is observe the same in the numerics. So by solving the Boltzmann equation in full, this is all done by that. But yeah, I understand your question. I think it's related to the mass splitting at some point being not too large.
Yeah, because in my paper, it seems not a necessary condition. And even without the chemical equilibrium, you can still have a bouncing phase.
No, indeed. Sorry. Yeah, I think that's a very good question. In the sense that this argument about chemical equilibrium is very useful, because if you write a relation of this type, this is very intuitive, and you can in fact derive even analytical expressions that help you to see what happens. Sorry. Yeah, I should have clarified. Of course, the physics is done not assuming chemical equilibrium, but just by solving the Boltzmann equation. Yeah, that's correct. So it's just very helpful to see analytical expressions and get what's going on, but eventually this is not strictly true anymore. Yeah, thank you for this.
Yeah. Okay.
Okay, very good. So this was the last picture. So we have the chemical potentials, okay. So this is the mechanism. Now, what I want to discuss a little bit is what potential implications this can have for phenomenology. This is also, in a sense, this is also related to the question that was just asked. So this is the same plot as before, and you can even get analytical solutions which really rely on the chemical potential relations that tell you that asymptotically the number density of chi, comoving number density, should be fixed by just half of the comoving number density of phi2 here, if you neglect this factor. And that's essentially the fact that two phi2s get converted into one chi at late times. But indeed, this is not really true. So if you look at the numerics, that's not followed precisely, because there are other effects. Chemical equilibrium is lost, as was mentioned, and also other processes come back. So for example, chi phi2 can become relevant enough to play a role. So in the end, this is a part. The final part of the evolution is really something where you need the numerical solution for, okay, which is what this is. But still, the intuition remains roughly the same. Okay, so this is the picture. So now, if we think of phenomenology in this simplified model, we have to think of two things. So here there is this chi is what I call dark matter, and this phi2 ends up with an abundance that is quite similar to chi. So this one could either be stable, so that we essentially have a two-component dark matter model, or we want it to decay, say, before BBN, so that we do not have to worry about affecting that part of that physics. And that's okay. This is a choice, a model choice in a sense. But what is not a choice is about phi1. Phi1 is a state that freezes out with a huge abundance, okay, many orders of magnitude above the one observed. And so we need this to decay. So phi here is a long-lived state, but at some point it does decay. So it's long-lived enough to go through this phase, but then it has to decay before we reach BBN. So roughly its lifetime has to be smaller than a second in very approximate terms. Okay, so this is in general a condition here that we have. And so yeah, Was there a question?
Yes, yes. So I have a question.
Yep.
Yes, so why pi number densities? I mean, why pi is freezing out so early than pi 2 and pi? What is the physical reason behind that?
I'm afraid I didn't hear the question. Could you repeat? Sorry about that.
Yeah, so pi 1 is freezing out much earlier than pi and pi 2, right?
Yeah, again, this is a very compressed plot. So of course, phi 1 still does participate in many interactions. Okay, so but yeah, in a sense, the final density is already fixed at XC to a very good approximation. Yes.
Yeah, so what is the reason? What is the physical reason behind that? I mean, why it just freezes out at much earlier temperature than pi 2 and pi?
No, I think this is
similar interactions, right?
yeah.
Except
So
nothing similar between pi 1 and pi.
yeah, so the issue here is that this plot, in this sense, that aspect is a little bit misleading, because what I mean here is that phi 1 at this point has already a very large abundance compared to the other guys, and say in this phase of the evolution it gets enormously enhanced. So phi 1 is still participating in interactions, but of course its total number density cannot change very much, okay, because there are so few phi 2s and chi's around that this is not really affecting it. So you would need to zoom a lot to see the evolution of phi 1 here. I think that's just the point, okay. The overall scale is fixed here, because then it's only interacting with the species that are extremely rare in the bath, if you want. Okay.
So the difference between the three curves at XC is only due to the mass differences, right?
Correct. It's only the mass difference. Yeah, indeed. So yeah, this I think relates also to your previous question. So I actually didn't catch the name of the person asking the question from the room, but does that answer? I think this is just a simple point.
But the masses are not particularly different, right? I mean, 300, 400, 500. They are not.
No, but it's an exponential. So yeah, sure. They are not very different, but it's an exponential of a e to the x, if you wish, e to the. I mean, it's still here. It's still a large. It's just purely kinematics, if you want. Indeed, it's just the masses here.
Okay, but what I'm saying is, like, intuitively, if we don't have the last interaction, like in your Lagrangian, the last interaction, pi 2 square, pi 1 chi. So let's suppose you don't have that interaction, and then we are assuming the same masses like 300, 400, 500. Then all the three should more or less have the same number density, right? Same freezeout number density, right? Because
no. They will have the same apart from an exponential factor, right? So if you don't have that interaction, what will happen essentially is that you do not have the bouncing phase, of course. So these will just keep falling along this one. Okay, so this continues down, and this one is here. And so you see that the difference between them will just be enormous at some point. Okay, eventually they will all freeze out, but even a small mass splitting can get you a very large difference in final number density. It's just an exponential, really.
Okay.
Yeah, we can come back to that. Yeah. So this is great. And the summary here is indeed the phi 1 has to decay. That's the message. So what can happen now for the phenomenology is the natural place to think of is indirect detection. And the reason for this is that the WIMP paradigm is associated with a number typically, okay, which is the canonical thermally averaged annihilation cross section, which is about 2 × 10⁻26 centimeters cubed per second. Now that's of course the simplest S-wave vanilla model, but it's still a number that is very, very relevant, okay, because it's a natural target for experiments. And here the observation is simple. If you have something like a bounce, then the cross section for dark matter annihilation to, in this case, the phi 1 and phi 2 can be larger than that. Okay, it can be significantly larger than the canonical value, because in a standard scenario, this would just give you you would just follow the equilibrium distribution for too long and freeze out with a very tiny abundance. But if after this you have a bounce, you go back up. And so essentially you can still recover the observed value, even though the cross-section is quite large. Okay? That's the idea. And so in general, in a setup like this, you would expect better prospects for indirect detection of dark matter. Okay? That's the qualitative statement. And this is a plot that's showing it. So this is a relatively busy slide. So let me go through it. This is the annihilation cross-section for chi to phi1. Okay, and phi1 will eventually decay to standard model. And in this plot, it's assumed that phi1 decays to WW. This is purely a choice. Okay, no, it's not preferred by the model. It's just one illustration. And this is indeed the annihilation cross-section versus the mass of dark matter. So you see a few important lines. The first one is just the canonical value for thermal WIMPs, which is 2 × 10⁻26, and it's here, this line. Okay, and then you see, for example, we can look at the solid black, okay, which is the prediction that you get for a bouncing dark matter in a certain case, which is the case where phi1 has a mass that is m chi over 2. Okay, it's a specific case. But if you do this, then this is the prediction that you have. And the other lines here, the dotted and the dashed, are variations over that, in the sense that what varies here is the kinetic decoupling between the standard model and the dark sector. In what I showed you so far, I always assume the kinetic coupling throughout for simplicity. But in a realistic model, you will have also a kinetic decoupling of scattering of dark particles and standard model particles. And for example, this dashed line is, this dotted, I'm sorry, is what happens in the Higgs portal. Okay, if you couple the two sectors with the Higgs portal and this mass range, you get this effect. So it's somewhat smaller. And these are the theory predictions, and the bottom line is this CTA line. Okay, so this is the Cherenkov telescope array projected reach on the, say, WW final state. And you see that the message is quite clear. You cannot reach the canonical thermal value in this mass range, but you can test several cases of this bouncing dark matter setup. Okay, so I want to stress that this is one example. Okay, it's not claiming that it's a general, and it does depend on the model, but it's still showing the point that you can get cross sections that are even, say, one or more orders of magnitude larger than the thermal value in such a setup. Okay, so this is interesting, and is one thing maybe to think about in the future, how to embed this in a more realistic and a picture, in a sense. This is really just a simplified model. Okay, this is what I just said. So for this cascade process that I discussed, so dark matter to phi1, and phi1 decay to WW, you do not reach the thermal target with CTA. It's not expected, at least, but you do test this. Okay, so that's the punchline. Now, in the next few slides, what I want to do is come back to the setup and sort of speak a little bit in defense of it, because of course this is was just a toy model. And so let me tell you a few things about it, but let me actually stop. Are there any more questions about the phenomenology or previous aspects?
Do you hear me?
Yes, absolutely.
So phi1 number density is huge in the beginning.
Yes.
So could there be a matter domination by phi1?
Good. Yeah, there could be. So there is not for the parameters. Yes, it is. So there is not for the parameters that I showed you. So in the plots that I showed and that we have in the paper, we checked that you don't reach a matter domination era, but in general, indeed, you could. So that's one of the things you have to take into account. Yeah, absolutely. Okay.
So phi1 decays. So phi1 to WW is a dominant decay mode.
Oh,
so
yeah, this is. Sorry, say it again.
So how fast is it, this process, decay process, phi1 to WW?
Very good. This is, let me just hold a second. I'm going to show you that in a moment. Okay, so okay. I will discuss a little bit the constraints. Yeah, of course, that's a good point. Let me just show you a couple of slides on the model. Okay. So
I have one question.
Oh, please. Yes.
So this detection process is not related to the phi1, phi2, phi2 chi or something, right? So do you really, from this detection, you can say it's bouncing dark matter or not. I mean,
There are many models.
So I didn't hear the second comment, but I did hear the question. Yeah. So I understand your point. Yes, this would be, let's put it this way. If you observe a indirect detection cross-section that is significantly larger than the thermal target, this is one of the possibilities. Of course, yeah, it's not going to tell you that this is the model. I understand your point, yes. That interaction is only enabling the bounds, so your cross-section to be larger than naively expected, but then to make the link, you need more information. Yeah, I agree with that. Okay, are there more questions or? Okay.
Can you make chi stable enough? I mean, chi can decay into phi2 and
Very good.
Right?
Another concept.
Very good question. So this is, I'm going to answer it in the next slide. Okay, so this is, yeah, we can, the answer is yes. And I completely agree with these questions because they're important. And this is why I need to go back to the model and tell you a few more things, because otherwise I agree this is too vague. So let me go back to that. Let me show you. So this is the same model as I was showing before, but now the scalars are multiplets under a symmetry that is this one. Okay, so let me take this symmetry. It's an SU2 times U1, a global symmetry, times a Z2, which just means I will ask even number of scalars everywhere. And the chi is a triplet of this SU2 with no U1 charge. The phi2 is a doublet with U1 charge, and the phi1 is just a singlet under everything. Okay. In fact, I want to stress this is really what you get, as maybe I'll come back to if I have time at the end. This is really what you get in a certain limit of dark QCD, or if you want even standard model QCD, you could get this for the mesons. So that's where this comes from. But more in general, you can have the structure, and you see the first line as just the couplings, chi squared, phi1 squared, and so on. And the second interaction in the second line is the one that matters for the bounce. So phi2, chi, phi1. And what is important and specific to this is that this is the only interaction that you can write that changes the number of particles. Okay, so if you try to write the others, they vanish by symmetry. And so this is the first statement. Okay, so this is what you get out of it. Second point, answering the question, is the stability. So of course that's very important. And in this case, both chi and phi2 are stable. They're stable because they are the lightest particles that carry a certain quantum number. So for phi2 is just the dark Q1, and for chi it's the SU2. Okay, so because you require this mass relation, okay, this means that 2m phi2 is larger than m chi, and so m chi cannot decay into phi2 star. Okay, so this is why in this setup they're both stable. Okay. In general, of course, if you change things, you'll have to make sure the chi is stable, but in remains long-lived enough. But in this case, it is stable. And phi1 instead is just a singlet, so that is the state that can and should in fact decay before BBN. So let me show a little bit the parameter space. And indeed, there was a second question about the lifetime of phi1, which was a good one. So let me assume the following interactions. This is a toy model, but I want to be concrete a bit. So let me assume that this is the Lagrangian coupling phi1 to the standard model. This lambda v is a Higgs portal, phi1 squared. This curly h is just a Higgs doublet of the standard model. And this is the one that was keeping thermal equilibrium at very early times. And then I will add this coupling to WW, which is just one option, with the coupling G bar. Okay, so this is the phi1, W mu, W mu. This is the only coupling that I wrote that breaks the Z2 symmetry. And this is the one that leads to phi1 decay. Okay. Now, to answer the question that we had before, what we require is this. So we require that the lifetime of phi1 is at most 1 second, so that it decays before BBN, and that's kind of obvious, but also that it is larger than about 10 to the minus 6 seconds, and that is because we want it to not be active during the bounce. Okay, so we want, for simplicity, we want first the bounce, then the decaying phase for phi1, and then say BBN, and later universe cosmology. It's a choice, but in this safe, at least in this range, it's very safe. That's the point. So this Z2 breaking from this operator has several effects. The first one is clear that this one mediates phi1 decay into W mu. And the second effect that is a little bit more subtle is that by closing a loop, you can also get a tadpole term for phi1 here. Okay, if you close the W loop, then you get a phi1 term in the potential. And this generates a VEV for phi1 generically that scales in this way. And in fact, if you plug the fact that phi1 gets a VEV here, you also get a decay of phi1 to standard model Higgs, if you wish. So Higgs bosons and longitudinal gauge bosons. So you have two contributions to the lifetime in general. And so if you look at the parameter space, this is how it looks like. So this I'm showing lambda, which is the cutoff of the theory, the scale suppressing this operator, versus G bar, which is the coupling in front here. Okay, and let me show you if there are a few things in this plot. Let me go through them. So the first, the most important is this region that is shaded in what is probably light green, I guess. This is the region where the lifetime of the phi1 is in the range that we want, 10⁻⁶ seconds to 1 second. Okay, and the shape is coming from the combination of longitudinal and transverse decay modes that have different scalings with the parameters. So you want to live here essentially in this solid region, and then we have other constraints. Okay, so there are lines here, and what you want to do is be below those lines. What's the point here? The point is that when you generate this VEV for phi1, you also generate trilinear interactions. Okay, and those trilinear interactions can, in general, enter the picture and change what I showed you. So what we do is require that they don't play a role, that they're small enough. Okay, by doing that, you need to be, for example, to require that the trilinears do not change the 2-2 scattering, which they could, then you need to be below this line. And you see it's quite safe. So the bottom line is, if you are in this region, okay, this is the bottom line, you can have a cutoff of the theory that is more than 10 TeV, so well separated, and a coupling G bar that is less than 10⁻⁹, which really means this is a very tiny perturbation to the picture, which is what you would expect also. Okay, so this is just a sanity check that what we showed is not clashing with something clear. Okay, so
Question?
Yeah, please.
Do you have a radiative generation of other quad couplings, for example, phi2 square h square or something like that?
Oh, let me see if I heard your question correctly. So you are asking if I generate radiatively phi and other scalars coupled to x h dagger h?
Yeah.
Yes, in general, I would say you have it, because you can just have, say, phi1 squared, phi2 squared, for example. Close the loop. Yes.
Is it safe or? Does it change your scenario or not? I'm just wondering.
You can take lambda really small.
No, yeah, I would not. So
It
depends a bit. It depends a bit on what we look at. So it will not, for example, from the cosmology point of view, it will not affect much the interactions between the dark sector and the standard model, because phi1 is far more abundant than everybody else. So in a sense, that's going to lead anyway. Were you thinking of other effects, maybe, of other pheno aspects? You say maybe indirect detection. This is what you had in mind.
Not just indirect detection, but previously we considered, for example, phi2 annihilation into the standard model sector annihilation, right? But
yes,
it can, if it's too efficient, then you may have much less number density of phi2, then this bouncing behavior would not be there. I'm just worrying.
No, I understand it. Yeah. So I agree with the point. In general, this will be something that one needs to check. I actually didn't check the numbers, so I cannot give you a quantitative answer. I would expect it to be small in the sense that it will still be at most order one coupling suppressed by loop. But in general, I agree with the comment. So thank you. Yeah, one has to take it into account. Yeah.
So if phi1 decays around VPN, so lifetime around 1 second, then could there be a meta domination?
Okay, so in general, the answer is yes, there can be a meta domination, and that would be potentially dangerous. For the parameters that I was showing you before in the cosmological evolution, that we checked that it doesn't happen. So the density of phi1 never gets to the point of dominating over radiation.
I mean, initially the Y number was around 10 to the minus 3, right?
Sorry, say it again.
So Y phi1 was around 10 to the minus 3.
Yeah. So it is. No, it is. So I agree with you that you have to check. I completely share the comment. And in general,
I trust you. It doesn't sound.
No. We did check that up to, indeed, say 1 second, which is the latest that it can decay. This is fine. Of course, I agree that in general.
Estimation, I mean, rough estimation, the rho phi1 is almost the same as rho radiation around bouncing time. Agree?
That's not what I remember. Although I need to do the estimate again. So, but I'm pretty sure.
If it's around 10 to the minus 6 seconds, you said, then 1 second, I mean, this domination could be significant. So that's what I'm worried. Probably I'm wrong. Yeah.
No, okay. We did check it, and let's do it this way. So that's a good point. I'm happy to double check it because it's important, and we can definitely be in touch after. We'll double check it. I remember doing it, but let's not do it online. Also in the interest of time. Okay.
Okay.
Yes. So in the last part, which is indeed a few minutes, what I want to discuss is other cases. Okay. So we focused on this model, which was an example. Now, what I want to show is that it can happen. The same mechanism can happen in other cases, and this will be just a sketch because we don't have the same level of detail, but it's still useful. The first example is a case where there is basically the same model, so very similar, but with two modifications which matter. The first one is that I'm going to assume that the mass condition that was critical for the bounce is now reversed. So 2 m phi 2 is lighter than chi and then m chi plus m phi 1. If this is the case, then we don't get the bounce in the same way as before. Clearly, that's not going to happen. But as a second assumption, I will assume that phi 1 decays earlier. Okay, so the phi 1 does decay around the time of freezeout. So it's now relevant in the region that I was focusing on. And this is a picture that you get. So let me focus in this plot on the solid lines. Okay, let's focus on the solid lines. And initially, the behavior is somewhat similar to what I was showing. Okay, you just have this common chemical potential for the states. But then what happens is that at some point here, phi 1 starts decaying. Okay, the lifetime becomes relevant. And so here we get this behavior. There is just the decay of phi 1. And so what happens is that because you need to keep this relation between the chemical potentials, again from the same process as before, you have the following effect. If phi 1 is decreasing because phi 1 decays, what you need to do is to increase m chi to compensate for this relation to hold, essentially. And so this is a very qualitative picture. Of course, the true answer is in numerics, but it helps. And so what happens is that phi2 to chi phi1 does win in this case, even though it requires thermal support. Okay, so this is not now the open direction. The open direction is chi phi1 going backwards, but nevertheless, this does populate a lot. This does proceed more favorably in this direction, and so you see indeed the bounce here for the chi density going up again. Okay, so that is the picture, and the dashed lines are a very similar picture, only changing the lifetime of phi1. You make the lifetime of phi1 10 times shorter, and it's just illustrating what happens. But you see that it's relatively similar in terms of qualitative features.
Hello. So sorry.
Yes. Yep.
So in this product, can you make the chi to be the dominant documented component?
The
dominant... I mean the chi, right? Because the chi is the bouncing document, right?
Yes, yes, it is.
But it seems that the density is subdominant in this product.
Oh, to phi2 here.
Yeah.
Yeah, I don't think that's a particularly general statement, in the sense that you see, if I go to the case with a different lifetime, I already get them to be much closer. So that may be dependent on the parameter point that we chose. I don't think it's general. So I would say in general, yes, you can. There is no particular issue. One thing that you do need to worry about in this case, and we didn't study it at all, but it's important to keep in mind, is that because you change this relation here, okay, now you have to worry about dark matter stability. Okay, so then it's a model dependent question. If I1 is very light, you could have a decay of chi and so on. Okay, so in general, indeed, there are issues to consider here. So take this as an illustration more than I'm not claiming that this is a full picture. And the second example should be the last. Yeah.
So in general, there is no way that all the dark matter can be bouncing. Phi2 also bouncing?
All the dark matter can be bouncing?
Yeah, is there no theorem like that, or interesting?
No, I think you can, in the sense that imagine the scenario that I was discussing before. You get chi and phi2 to freeze out with the comparable abundances, but you can definitely have interactions that make phi2 decay as well. Okay.
Make phi2 decay.
Yeah, and that would not be, if it decays slowly, that would not be problematic. We checked this actually. We have estimates, and it doesn't affect the stability of chi. There are regions where you can make phi2 decay. Chi remains very long-lived.
But anyway, the point is that you need phi2, which must have larger density than the chi.
Yes. No, I understand. So you can have several things. What you can also have is a crossing of the lines. So there are some parameter points where the freeze out of chi is very close to the one of phi2, or even slightly higher. But in any case, yeah, in some sense, if you really want chi to be 100% of dark matter, you maybe need phi2 to decay eventually. Yeah, it does have to be there. Well, at least one other state has to be there. Yes.
But once you make phi2 to decay, then
yes,
chi will also decay.
Correct. This is what I was saying. Yes. But there are regions of parameters, and we actually have a discussion of that in the paper, although I don't have it in the slides.
Okay.
You can make chi very long-lived and phi2 decay, and it's consistent. So you can, depends on the masses and the.
But your SU2 symmetry should be broken explicitly in order to make phi2 decay.
The Z2 has to be broken explicitly, but also you can, yeah, sure.
No, I meant SU2.
Oh, sorry. SU2 has to be broken. Actually, phi2 is stabilized by the U1. So I think you need to break the U1 symmetry. But yeah, no, indeed, you do need to introduce interactions of that type. Okay. So since I'm running out of time, let me just go to the last topic, which is another variation of this. And that is coming from, so it's a bounce, but for a 3-2 process, okay? This is in a sense a simpler setup because we only have two states. So there will be chi, again, dark matter, and just another scalar phi. So what I'm going to assume is the following thing. So m chi is heavier than m phi, is larger than m phi, but twice m chi is smaller than 3 times m phi, which means really the two masses aren't too far apart. Okay, clearly that's what we need. And let me assume as a toy example that I have only one interaction in the dark sector, which is a chi square phi cube interaction, okay, a 5-point interaction of this type. If I do that, then this is what you get as a behavior, okay? So this is the same y versus x. Notice though that the mass range is now very different, okay? I'm looking at the tens of MeV, and this is just because essentially to get the Rayleigh density in this for this type of process, you do need to be around this as a rough mass scale. And in the initial phase here, what you have is that the chemical potentials are still equal to 0 here. And this is because a process like this one, phi chi going to phi chi, is open and fast compared to Hubble. So clearly the number density, this combined with other processes means that you just get 0 chemical potentials for everybody. But then this vertical line is when the bounce happens. And the bounce here is defined as when only the process of 3 phis going to 2 chis becomes active, okay? It remains active, sorry. And this enforces, again, a relation of the chemical potentials here. And this relation is what drives this increase of chi, which then eventually freezes out, okay? And so you can also get, by assuming this relation of the chemical potentials, you can also get an approximate solution that is rough, but does show you that the relation you need of the masses is really that 2m chi should be lighter than 3m phi. If it's true, then this exponential is positive, and you do get the bounce. Okay, so that's the picture. And now let me just make a few comments about this, because this is again really a toy model, and so considerations for trying to embed this into a bigger picture or a complete model are the following. So the first one is how do you get chi square phi cube to dominate over quartics, chi square phi squared? And this is just a sketch of how one can imagine doing it. Okay, so here the idea is that you have you assume that chi and phi communicate only through a mediator S. Okay, so these are two secluded sectors. Chi is here and phi is here, and only S is mediating interactions, and that S has the same numbers, quantum numbers of chi, so that essentially you can write an interaction of like this. Okay, this is not suppressed by anything, but if you want to write a cubic interaction in the UV, you need to break the phi number. Okay, these are all complex scalars in this idea. So if you integrate out S in the low energy theory, what you get is both 5-point and 4-point interactions, but there is a hierarchy in the sense that 4-point interactions scale like epsilon squared, this small breaking, and 5-point interactions scale like epsilon. Okay, so this is one sketch, and really a sketch at this level, of how you can imagine that there is a hierarchy between these two. But the second comment, which was also brought up by you guys, in fact, is the fact that in general, if you even starting from a 5-point interaction, you generate 2-to-2 processes at 2-loop level. So this is the class of diagrams you do generate. And of course, in general, you have to be careful, because a process like chi to phi phi can wash out what I showed you. Okay, so this is important. These are the references that show this, in fact. And I think this is interesting. We haven't worked on this in any detail, but I think there are questions that for a model, from a model point of view, are interesting. In particular, the question is how do the 3-to-2 and 2-to-2 are related. Okay, this requires you to write down a model to know if there is, for example, if both processes are S-wave or there are further momentum suppressions and so on. And also will depend on the symmetries of the model, if you have reasons why you cannot generate 2-to-2 processes or so on. But this is indeed a model dependent question, and I think it's a very interesting comment to think about. So at this level, one needs to do, I think, work to embed this into a picture that is self-consistent. And so let me, in the interest of time, conclude. Okay, so what I showed you was this mechanism for thermal production of dark matter that we called bouncing dark matter. And it's really a transition from an exponentially falling to an exponentially rising equilibrium curve. That's the statement. The requirements are in particular that the chemical potential of dark matter, which is a useful quantity, we think, in this context, has to deviate from that of other species. And also it has to rise fast enough for the bounce to occur. From the pheno point of view, one expectation is related to annihilation, so indirect detection. I showed a few examples, okay, which were different from each other with different interactions. But I think a very interesting question is also from a model point of view is to think where else this could arise, either in setups that have been already looked at or thinking of other ideas. And I think this is a direction to go forward. So with that, let me stop and really thank you for inviting me again.
Thank you for the nice talk. Any question?
I have a question. Do you hear me?
Yes, I can hear you very well. Thank you.
Okay. My question is very naive. Please go back to the 10 page.
Page 10?
Yeah, page 10.
Yes, 10. Sorry, I will have to scroll back a lot, but I'm getting there. Yeah.
No. Please go to 12 page 12.
Apologies.
Yeah.
Yes.
In this plot, I understand that if x is going to be larger, then the time is passing, right? From
yes.
Then by the way, in the division of x, the larger t is temperature, right?
The larger t is, yes, it is temperature.
Yeah, then if x is larger, then the temperature is going to smaller, right?
Yes.
I don't understand. Why the temperature?
No. Sorry.
No,
Let me explain. So in this plot, time goes from left to right.
Yeah.
And temperature decreases from left to right. Okay, this is just the expansion. Yeah. So this is assuming, all of this is assuming a radiation domination. And so on. Yeah.
And the next question is, there are three critical points, XC, XB, XF, right?
Yes.
Then I think this point cannot be determined by only using the masses of particles phi 1, phi 2, chi. Is there any values to determine these three exit points, chemical potential, or?
Yeah. So if you want, for XC, the first one, this is really just when the dark sector and standard model go out of chemical equilibrium. So you can take this process, say phi 1 to standard model, and ask when this one goes, the rate for this goes below Hubble. Okay, it's beaten by the expansion. So that's the first. The second is there are several ways to define it. You can use the chemical potentials, for example, but also you can ask when this departs from this shifted equilibrium. So it's again sort of a departure from.
I don't know whether I understand or not, but the first point, in order to get the first point 10, then the temperature should be 50 GB, right?
That is correct. Yes, 500 divided by 10. Yes, 50.
How can I the temperature? How can I the temperature 50?
Sorry, let me understand.
Yeah. At the first point, the x value is 10, right? Then
Yes.
Then since the mass of chi is 500 GB, the temperature must be 50 GB.
Yes, correct.
Yes, yes. So my question is there any values to determine the temperature? I think if we see only this plot, we can determine the temperature value because there are only the masses of particles.
Sorry, I'm not completely sure that I follow, but what I'm saying is the following. So let me say that I know the dark matter mass, 500 GeV, and I know the masses of the states.
Yes.
Then these x's, or in other words, these values of the temperature are determined dynamically. So I'm asking that some process, in this case, it would be annihilation to standard model, goes out of equilibrium. Goes out of equilibrium. I compare n phi 1 sigma v for this process to Hubble, and when the two are equal, that's giving me the temperature of the coupling. So it's a dynamical statement, of course. It's just determined by the dynamics.
Dynamics. We need to know. We need to determine the dynamics, such as coupling constant or.
Yes.
That?
So you need to. Yes, it will depend on the value for the sigma v for the thermally average cross section.
Yeah. Then after that, we can determine the temperature, right? If we determine several dynamic or coupling constants or.
Yes, then we.
Yeah.
Then we can determine the temperature.
Yeah, we can. Okay, thank you.
Oh, thank you. Yeah.
So for the benchmarks you've picked, do they somehow maximize the bounce? Do you know what kind of mass, the ratios of the masses you need to get the largest possible bounce or anything like that?
Yeah, so in some sense, yes, in this plot, this is chosen to make the bounce very prominent. That's correct. So you can make an argument, which we have. I don't think I have it in the backup. No, I don't. But yeah, you can estimate how much you can get, and I think if I remember correctly, the best situation, meaning the largest enhancement, comes when you have a very light phi 1, compatibly with the other conditions, and then you can see that you get up to, I think we estimated roughly even 10 orders of magnitude in principle of bounce. Okay. So indeed. Yeah.
Okay, thank you.
Thank you.
Other questions? Actually, I have one question. In your 3-to-2 process, what was the alpha effective? Maybe I missed.
In the 3-to-2 process, yes. Let me go back. What was the? Say it again.
What was the alpha effective?
Oh, alpha effective here, 0.4 for this plot.
Yeah. Yes. But why is that? No. I mean, the definition of alpha effective.
Oh, sorry. Yes. No. Because you're right that I didn't define it. So here, what I'm doing is saying that in general, I expect this scaling, with couplings. Okay, with couplings. So I parameterize this in general. If I just have a 3-to-2 process, I'm not even saying where it comes from really. If I have a 3-to-2 process, I expect in the S wave, I expect a scaling of this type with couplings. You can estimate it, and you just get 5 powers of the mass, and then you are left with essentially 3 powers of an alpha coupling. Okay, and that is just defined by this equation. Okay, I'm not saying where it comes from. So in a sense, this equation defines alpha effective. Okay, and 0.4 is just the value that I need in order to reproduce the relic density for chi.
Then let me change the question. So to get the 0.4 alpha effective equals 0.4, what is the how big the effective coupling of y square chi cube?
E will be it's an order 1 value, right? In the sense that the order 1 alpha effective will be some coupling square times 4 pi. Okay, and that coupling will be, roughly speaking, of order 1 in order to get here. This, of course,
It is a typical scale for a simple dark matter. Coupling.
Yes.
That is. Sorry, I don't know about sim, but is how why is the dimension parameter of that? I mean, divided by what?
Sorry. Okay.
So the effective coupling.
You mean
I mean, it's order 1 by.
Yeah, it's order 1 or 10, even 10 something.
I mean,
He's asking the dimension.
Dimension.
Dimension is.
Then.
So you have to divide by the m5 to 5th power.
No, I mean, I know. Never mind.
No. Let me just. So what I meant by dimensions is that alpha effective here you can write it as some coupling g, okay, squared divided by 4 pi, and that g to get 0.4 is, roughly speaking, of order 1, of order 2, is an order 1 number, and okay, so it is indeed, as was mentioned, you expect in this mass region to need large couplings because the SIMP needs in the tens of MeV needs order 1 alpha, if you want, an order 1 coupling. So that's the rough range. But again, I am not claiming that I wrote down a model that gives me that. So I didn't do that. Okay, so it's just a rough range to keep in mind.
Any other questions? If not, let's thanks Peter again. Thank you very much for having me.
Thank you.
Okay, let me press the stop button first.